Hello students, welcome to my class. In my last lecture, I was discussing about the theories related to solid state. Today, I am going to discuss few questions related to your chapter, that is the solid state. And the questions are from your NCERT textbook exercise, so that you can practice this question and definitely it will help you a lot during your board examination. So friends, let's start the topic. That is, look at the question number 1. Listen carefully what is given here. What makes a glass different from a solid such as quartz? Under what condition could quartz be converted into glass? Again I am repeating. What makes a glass different from a solid such as quartz? Now listen carefully. What is the answer of this question? This is a single marks question. Glass and quartz. Quartz is a crystalline solid in which SiO2 tetrahedra arranged in regular pattern. What I am telling, arranged in regular pattern. That is, in this case there is a long range order. That is, SiO2 tetrahedra arranged in regular pattern and long range order. But if I talk about glass, glass is a super cooled liquid. Again I am repeating, glass is a super cooled liquid, or you can say amorphous solid. Amorphous solid. What I am telling, glass is a super cooled liquid or amorphous solid in which, listen, in which that is SiO2 tetrahedra are arranged in irregular pattern. Are arranged in irregular pattern. This is the case, my friend. Arranged in irregular pattern, which makes glass a amorphous solid. That is super cooled liquid. It has a tendency to flow. For example, that is, we can say that is short range order, my friend. Wait for a moment. Short range order. Clear? This is the case. Now, what condition could quartz be converted into glass? That means to say only the temperature plays a role to convert quartz into glass, my friend. If you decrease the temperature, then definitely quartz will be converted into glass, my friend. This is a simple question, only 1 mark question. Then you have to reply in a restricted, in few words only. Clear to you? Now let's move to the next question. Wait for a moment. Now let's move to the question number 2. This is 2 marks question. Now listen carefully what is given here. Classify the following solid in different categories based on the nature of intermolecular force operating them. Do you remember, as I have discussed during my lecture, that is, there is ionic solids. Yes. If there is a electrostatic force of attraction, electrostatic force of attraction between the particles, that is between ions, my friend. That is, in this case, in ionic solid, the constituent particles are ions, my friend. That is one cation and the second one is, my friend, anion. This is the case, cation and anion. Now, if I talk about this, first of all, potassium sulfate, that is K2SO4. As we know, potassium sulfate consists ion, that is 2K plus and SO4 2 minus. That means to say, if there is a constituent particles are ion, then it is an example of, my friend, ionic solid. So, potassium sulfate, if anyone asks you about potassium sulfate, we can say this is ionic solid. So, right here about ionic solid, first one is, my friend, that is K2SO4. Now, tell me tin, no, benzene, urea, ammonia, zinc sulfide, again metal, that is ZnS. ZnS is also, my friend, ionic solid. Graphite, rubidium, silicon carbide. No, ionic solid are K2SO4 and ZnSO4. Now, there comes, my friend, metallic solid. What do you mean by metallic solid? Those type of solid in which the constituent particle are metal atom, that is, and in this case the bond operating is metallic bond, my friend, metallic bond. Clear to you? For example, that is the bond is metallic bond like this. Do you remember? Wait for a moment. This is how the metallic bond forms, that is the metallic bond. Now, metallic bond in which cases? The second one is, I am writing here, my friend, metallic solid. Metallic solid, that is tin. Tin is metal, we can write here tin, that is Sn, tin. Now, benzene, benzene is not a metal, urea is not metal, water, zinc sulfide, no, graphite, rubidium. Rubidium is also a metal, my friend. So, this is the example of metallic solid. Now, there comes, my friend, the third one is molecular solid. What do you mean by molecular solid? The type of solid in which the constituent particles are atoms. What I am telling? Constituent atoms or molecules. Yes, sir. Again, I am repeating, the type of solid in which the constituent particles are atom and molecules. In this case, molecular solid are categorized as polar, non-polar. Do you remember? Polar molecular solid, non-polar molecular solid, and hydrogen bonded molecular solid. Do you remember this? In this case, this always happen when there is an involvement of non-metals, my friend. What I am telling, when there is an involvement of non-metal. If I write here benzene, benzene forms by non-metal like C6 acid. It is an example of molecular solid. Urea, as we know the formula of urea, NH2 CO NH2. It is also a molecular solid, my friend. Ammonia, NH3 is here also the molecular solid, because N is non-metal and hydrogen is also non-metal. Put here NH3, and NH3 is hydrogen bonded solid, my friend. C6H6 is non-polar molecular solid. These are the cases. Water, again hydrogen bonded solid. Put here, that is a molecular solid. Now, next one is graphite and argon and silicon carbide. Argon, as we know, in argon there is also the London force and dispersion force operating. This is also known as non-polar molecular solid. Clear? Now, there comes, my friend, the next one. Is it visible to you? The next one is, my friend, different. That is the covalent or network solid. If anyone asks you What is covalent or network solid? The simple explanation, giant-like structure, my friend. If I talk about graphite, giant-like structure, hexagonal, three-dimensional structure. If I write here silicon carbide, these all are the example of covalent or network solid. I think we have categorized each and everything: ionic, metallic, molecular, and covalent or network solid. Silicon carbide, rubidium, argon, graphite, we have done the thing. That is a complete classification. I think now you are familiar with this type of questions, and definitely if you have a proper explanation related to any question, then you can solve each and every questions, my friend. Am I right? Yes sir, you are absolutely right. Now I am going to rub this part. Let's move to the next question. What is the next question? Listen carefully. In a compound, this is a numerical based question. Wait for a moment. Solution of this question. In a compound, nitrogen atom makes cubic close packed lattice. What I am telling, nitrogen make cubic close packed lattice, and metal M occupy 1/3 of the tetrahedral void. Determine the formula of the compound formed by M and N. It's very simple. Let the number of nitrogen atoms per unit cell is equal to 4, because CCP, or if you do not know, put here X. Clear? If the number of atom per unit cell is 4 or X, therefore number of tetrahedral voids. Tell me what will happen. Number of tetrahedral void will be equal to 2 into 4 equal to 8, or you can write 2x if you do not know the number of atom per unit cell. Now what is given here? That is, the metal atom occupy 1/3 of the tetrahedral void. So the number of M atom per unit cell in this case, then we will write here 8 into 1 by 3. That is, my friend, 8 by 3. 1/3 given here, number of atom, number of tetrahedral void is 8, 1/3 8 upon 3, or you can write here 2x divided by 3, whatever the situation. Therefore, the formula, now what is the formula in this case? We can easily write here. Therefore, the formula equal to metal into nitrogen. Metal here we can write 8 by 3, then here 4. So that will be equal to M8 and 12, or you can write simplest ratio M2 and 3. This is the formula, my friend. M2 and 3. By using X, you can also write down the formula. Suppose if you do not know, then write down the formula in this case. M tends to N. M is my friend 2x by 3 and x. This one will cancel this one. What we get? M2 and 3, my friend. This is again the formula. So formula is M2 and 3. This is 2 marks question, frequently asked question. Check these things, my friend. These are the things. Okay. Now I am going to rub this part and we'll discuss the next question. Wait for a moment. Now if I modify the question, now if I write here a compound, listen carefully, here is given, in a compound nitrogen atom makes cubic close packed lattice and metal M occupy the 1/3 of the tetrahedral void present and 1/3 of the octahedral void. If I add here the question, then what will you do? Octahedral void. both 1/3 of tetrahedral and both 1/3 of the octahedral void. Now what will you do, my friend? How to give the answer of this question, my friend? Yes, definitely. Number of n atoms per unit cell, mark it as X. Yes, sir. That is the nitrogen atom. Yes. Number of octahedral voids. Tell me, the number of octahedral voids is equal to X, and the number of tetrahedral voids will be equal to, my friend, 2X. Yes. Now, therefore, number of m atoms, what will happen in this case? Tell me, number of m atoms. 1/3 of the tetrahedral void and 1/3 of the octahedral void. That is the case here. Yes, sir. Now, what will happen? 2x by 3 plus x by 3. When we take common 3x upon 3, that is we get x, my friend. Am I right? Look at the things. 3 common, 3, 2x plus x, 3x upon 3 is equal to 3. Now what will happen in this case, my friend? That is the formula equal to m into n, x into x, my friend. That is the formula here is mn. If you, again I am repeating, if you change the pattern, then doesn't matter. We have to follow the similar trend and you can easily solve the questions, my friend. Wait for a moment. Let me check the things. Now let's move to the next question. What is the question number 4? Again this is a numerical based question, and what is the question given here? Listen carefully. Given here, gold crystallizes a face centered unit cell. What is given here? Gold crystallizes a face centered unit cell. Now what is the length of the unit cell? It is given here FCC. FCC, clear to you? In FCC we people know R is equal to A upon 2 root 2. So A is equal to, we will put here 2 root 2 into R, 2 into 1.414, and what is the value of R? 0.144 into 10 to the power minus 9 meter. If I solve this, we get the value of A, that is the side of the unit cell. And do you remember from where this derivation comes? Yes sir, we do, because as I discussed during my theory lecture, that is, this is the case. Yes sir, this is the case. Now this one, this one, this one and this one. Now the particles are present at corners. The particles are present at corners. This is the case. The particles are present at corner and particles are also present at the face center also, my friend. This is the case. Do you remember? Yes sir. I am taking this example. Mark here, that is A, B and C. What will happen? It looks like this, my friend. 1, 2 and here is 3, and start from here, this one. Now here is also a particle like this. This is the next one, my friend, and again this 2, this is the next one. Clear? So what we get here, the overall by including the particle we get, that is the this much line. Clear? And this much, that is this comes from 1, 2 and 3. That is, my friend, this one is R, this one is R, R and this one is R. So what is AC? AC is equal to, my friend, R plus R plus R, 4R. And what is AB, my friend? AB is, my friend, if I put here AB from 2, that is R plus R, 2R. Now this looks like right angle triangle. If there is a right angle triangle, then we people know that is, my friend, AB square plus AC square, AB square plus BC square is equal to AC square, and A is the side, AB is equal to the side of the unit cell. Now put here A square plus A square is equal to AC, that is, my friend, AC is equal to what will happen, R 4R square. Now put here, that is, we can write here, or root under a square plus 2a square is equal to 4r. We can write here root 2a is equal to 4r, or a is equal to, we can write here 4r upon root 2, that means to say 2 root 2r. This is the derivation. Clear? I think you can easily solve this question. These are very simple and easy to handle, my friend. Now wait for a moment. Let's move to the next question. What is given here? The next question, listen carefully. This is the question number 5. Now, what is given here? In terms of band theory, what is the difference between a conductor and an insulator? Now, listen carefully. What is the description here? The band theory. As we know, there is a conduction of electricity. That is, if the electron easily moves from valence band to empty conduction band. This is the situation. Empty conduction band. Clear, my friend? What is given here? This is empty conduction band and this is, my friend, valence band. Clear? If electron easily jumps from conduction valence band to the empty conduction band, then they are good conductor of electricity, my friend. What will happen if there is no gap? If there is no gap between empty conduction band, what I am telling, my friend, if there is no gap between empty conduction band and filled valence band, then we will say, in this case, my friend, they overlap each other, that is, electron easily jump. So in case of conductor, there is no gap between valence band and the empty conduction band. This is the explanation according to the valence band theory. Now, if this is, my friend, that is the empty conduction band and this one is the valence band, if there is a gap between, large gap, but I am telling, my friend, listen carefully, if there is a large gap between the valence band and the conduction band, that is, the electron now not easily available to jump from valence band to conduction band, then these are, my friend, insulator. Again I am repeating, then these are known as, my friend, insulator. I think theory you can easily write. Now between the conductor and a semiconductor, the same thing here. If there is a, I am moving here, if there is a small gap between the valence band and empty conduction band, again I am repeating, if there is a small gap between the filled valence band and the empty conduction band, then what will happen in this case? We tell, that is, this will act as a semiconductor, and further modification by introducing impurity or by introducing the temperature, we can modify the conductivity of the semiconductor, and this gap, the gap is known as, my friend, forbidden zone, and this is known as, my friend, band theory. What I'm telling, this is known as, my friend, forbidden zone, and this is the band theory, my friend. I think now you are very much familiar with this topic, and rest up to you how to define this thing. If you have a command over the theory, that is, if you have a complete representation, then you can solve each and every question related to the questions, my friend, related to any questions. It's up to you how to approach the questions. Clear, my friend? Now let's move to the next question. Now, what is the next question, my friend? Wait for a moment. Give me a few seconds. Now, here, this is the question, the solution of this question. Listen, a compound form hexagonal close pack structure. What is given? Hexagonal close pack structure. What is the total number of void in 0.5 mole of it? How many these are tetrahedral void? What is given here, my friend? Hexagonal hexagonal close packed structure. Given here? Yes, sir. It is given here, that is, it has hexagonal close pack structure. If it has hexagonal close pack structure, then definitely the number of voids here, this is a memory based question, number of voids here, my friend, 3. That is, number of octahedral void in this case is, my friend, 1, and the number of tetrahedral void in this case is equal to 2. Total number of voids is 3. Now, what is the total number of voids in 0.5 mole? As we know, 1 mole consists 6.022 into 10 to the power 23 molecules, or you can say 10 to the power 23 units. And here is 0.5 moles, that is, it will be equal to 1 by 2, because 0.5 is equal to half, is equal to 6.1 by 2 into 6.022 into 10 to the power 23. That means to say 3.011 into 10 to the power 23. Clear? Now, as we know, these are the particles present in 0.5 mole, and number of voids here is 3. So, therefore, total number of voids in 0.5 mole is equal to, that is 3 multiply 3.011 into 10 to the power 23. This is the answer. Again here is given the number of tetrahedral void, that is, number of tetrahedral voids. Clear to you? Number of tetrahedral voids is equal to, my friend, we will put here 2 multiply 3.011 into 10 to the power 23. This is the answer, my friend. And definitely it will help you a lot. Clear to you? So, I am giving you few seconds to note this answer. Clear? I think, friend, you have noted it down. Let's move to the next question. Wait for a moment. Now, the next question is, listen carefully. Explain the following with suitable examples. If it is given here, ferromagnetic, paramagnetic, ferrimagnetic, antiferromagnetic, 12 and 16 and 13 and 15 group compound. As we know, if there is a spontaneous or if there is a direction of the alignment of the magnetic moment of domain is same, like this. Do you remember? If the alignment of the magnetic moment of direction is same, that is spontaneous, that is 1, 2, 3, 4, 5, 6, 7, 8, then this is called ferromagnetic substance. Am I right? Yes. What is paramagnetic substance? Do you remember? Yes sir, we do. If a magnetic has permanent magnetism and strongly attracted by the magnetic field are known as paramagnetic, and the phenomena is paramagnetic. This is the general definition in terms. If any molecule or any substance contains unpaired electron, what I am telling, unpaired electrons, then they are paramagnetic in nature, my friend. Paramagnetic in nature. Do you remember? Yes sir, we do. Then they are paramagnetic in nature. For example, if I talk about Fe2 plus, Fe3 plus, Ni2 plus, they are paramagnetic because they contain unpaired number of electron. And what is the value of magnetic moment? Root under n plus 2 Bohr magneton. What is, my friend, n? N is number of unpaired electron in this case. Now there comes ferromagnetic, my friend. If the alignment of the magnetic moment of domain is unequal, parallel and anti-parallel, my friend, then we can say they are ferromagnetic in substance. That is, they have net dipole moment, they have net magnetic moment in this case. If anyone asks you anti-ferromagnetic, if the alignment of the magnetic moment of direction are opposite to each other, that is, they will cancel each other, then we can say, my friend, that is, they are anti-ferromagnetic. Ferromagnetism, ferrimagnetic and anti-ferromagnetic. This is a general definition. I have discussed this thing during my lecture also, my friend. Now 12, 16 and 13, 15 compounds. If I talk about when the binary compound forms by group 12 and group 16 elements, they are known as 12-16 group compound. For example, if I write here CDS, ZNS, these are group 12-16 compounds. Now the binary compound formed between group 13 and group 15 elements are called group 13-15 element, my friend. If I write here ALN, this is the group 13. Group 13 contains aluminum, group 15 contain nitrogen, my friend. These are group 12 and group 16. I think now you are very much familiar. That is the 4 marks question, 5 question. You have to just reply them with a point wise, that is because one part carry only less than 1 marks, so no need to explain more. You just need to explain like this way, that is differentiation easily possible. You can differentiate whether it is ferromagnetic, whether it is paramagnetic, whether it is ferrimagnetic, or whether it is, my friend, that is anti-ferromagnetic. Clear to you? Now I am going to rub this part, my friend, and we will discuss the next question. Wait for a moment. Now the next question, listen carefully. Calculate the efficiency of packing in case of simple cubic, body centered and face centered. This is one of the most important question, my friend, VVI question. Simple cubic, as we know, efficiency will be around 52 to 54%. 52 to 54%. Body center, the efficiency is around 68%, and for face center the efficiency is around 74%. You can easily calculate, my friend. Now I am giving you idea. Do you remember? I will discuss these things in my lecture class also. If there is a simple cubic given here, listen carefully, simple cubic, then what will happen? This is the case. Again I am repeating those things, and definitely it will help you a lot. This is the case. This is the simple cubic. Particles are only at the corner, my friend. This is the case. Particles are only at the corner. Am I right? Yes, particles are only at the corner. That is, if this is A, that is length of the or you can say let the side of the unit cell is A, and this is the particle, that means to say it forms like this, my friend. Yes sir. Now this one and this one, this is completely A. Yes sir. As we know, A is equal to R plus R, 2R. This is the relation, or you can say R is equal to A by 2. Yes. Now we know, I am moving here, that is packing efficiency. Again I am repeating, packing efficiency is equal to Z multiply volume of the sphere. What is the volume of the sphere? 4 by 3 pi r cube upon volume of the cube is equal to A cube multiply 3. As we know, for simple cubic, Z is equal to 1. 1 multiply 4 by 3 pi r cube. Now we people know A is equal to 2r whole cube multiply by 100. Now what will happen, my friend? Put the value 4 by 3 into 22 by 7 into r cube divided by 8r cube multiply by 100, my friend. That means to say this will cancel this one, 4 to 8, that is 11. That is, my friend, 1100 upon 21. Clear to you? What I am telling, that is 1100 upon 21. What is the value we will get here? That is 105, that is 5, that is 2, that is 8, that is 3, 52.3% around. So we can say in case of simple cubic, the packing efficiency is, my friend, 52%. Am I right? Yes sir, you are absolutely right. Now what is the case of face center? There is a particle here. Yes sir. Now if there is a particle here, now that is what will happen in this case? Do you remember? Now there is a particle, here is particle, and here is particle. In this case, now mark it, that is A and C. We will write here AC is equal to 4R, and this is, if I join them, then this is a right angle triangle. We will write here B. We can write here AB square plus BC square is equal to AC square, or AC is equal to root under AB square plus BC square. Do you remember? Yes sir, we do. Now what will happen? Put here AC is equal to 4R, AB, that is the length of the side, that is A square plus A square. Yes sir, definitely, that is 4R is equal to root under 2A, or A is equal to, my friend, 4R by root 2, or you can put here 2 root 2R. Now put this value here and here for face center, Z is equal to 4. If you put this value, then definitely you will get the answer. Similarly, for body center, the particle reside here. This is the body. Now mark here, that is D. this is the particle, and in body center what will happen, we will get R is equal to root 3 by 4a. Put this value and Z is equal to 2, you will get the packing efficiency. During my lecture I have given you the detailed information, and I think now you can easily solve such kind of questions, my friend. Now wait for a moment, give me few seconds. Now let's move to the question number 9. An element with molar mass, listen carefully, an element with molar mass 2.7 into, this is the first part of the question. Let me solve the first part of the question. An element with molar mass 2.7, m is equal to 2.7 into 10 to the power minus 2 kg per mole, okay. Now forms a cubic unit cell with edge length 405 picometer. A is equal to 405 picometer, that is 405 into 10 to the power minus 12 meter. If the density rho is given 2.7 into 10 to the power 3 kg per meter cube, yes sir. Now what is the nature of the cubic unit cell? That is, we have to find the value of Z, my friend. Z will come 4, that is, we have to find the value of Z. As we know, relate them, as we know, density is equal to Z upon M upon AQ into NA. What is NA, my friend? Avogadro number. Now here is density, density is given here, that is 2.7 into 10 to the power 3. What is Z? We have to find the value of Z. What is M, my friend? 2.7 into 10 to the power minus 2. Now upon A cube, what is A cube here? That is 405 into 10 to the power minus 12 whole cube. What is Na, my friend? 6.022 into 10 to the power 23. Now we have done the everything related to this question. Clear, my friend? That is, now if you solve this problem, then definitely you will get the answer. An element with molar mass 2.7 into 10 to the power minus 2 kg per mole forms a cubic unit cell with edge length 405. Edge length is given 405. If density per kg, yes, then solve, you will get the value of this question. Am I right? Yes sir, this is the detailed solution. I am going to rub this part, my friend, and we'll discuss the next part of this question. This is a simple question, completely theory based. If NaCl is doped with 10 to the power minus 3 mole percent of SrCl2, what is the concentration of anion vacancy? As we know, 1 Sr2 plus ion create 1 cation vacancy. What I am telling, create 1 cation vacancy. Am I right? Now if NaCl is doped with 10 to the power minus 3 mole percent of SrCl2, that means to say 100 mole of NaCl is doped with 10 to the power minus 3 mole of SrCl2. Therefore the concentration, what I am telling, my friend, therefore the concentration of cation vacancies is equal to, what is happened, 10 to the power minus 3 divided by 100 multiply by 6.022 into 10 to the power 3. This is the Avogadro number. Total overall we will get the concentration of cation vacancy. This is known as, my friend, impurity defect. Do you remember? This is the case like this. This is a crystal defect. In my lecture I have discussed everything about this. Suppose this is a NaCl crystal. Put here Na plus Cl minus, Na plus Cl minus, then Na plus and Cl minus, then what will happen in this case? That is Na plus, then here Cl minus, Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus, Na plus, Cl minus and Na plus. When it is doped with SrCl2, what will happen? SrCl2, that is Sr2 plus, will break like this, plus 2Cl minus, and this Sr2 plus has, look at, plus 2 charge, so it will displace 2 Na plus ion and occupy one site, and another site is vacant, and this type of defect is known as, my friend, impurity defect. So one Sr2 plus ion create one cation vacancy. This is cation vacancy. So what will happen? 10 to the power minus 3. So concentration of cation vacancy is equal to 10 to the power minus 3 divided by 100 multiply 6.022 into 10 to the power 23, my friend. Am I right? Yes, sir. These are the things related to this topic. Now I'm going to rub this part, my friend, and we'll discuss the next part of the question, and definitely this part is so much important for you. And what is the important point over there is, listen carefully. That is the last part. Explain the following term with example. What is Schottky defect? Do you remember? 1, 2, 3, 4 and 5. Let me draw the figure. This is the case. Now here is cation and anion. What is Schottky defect? When equal number of cation or anion leaving the site. Suppose this is like A plus, B minus, 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 and when equal number of cation and anion leaving the site, that is known as, my friend, Schottky defect. Due to the Schottky defect, there is a decrease in density take place, my friend. What I am repeating? Because the particle leaves the site, and Schottky defect will show by those compounds which have high coordination number, and the size of cations and anions are equal. Again I am repeating, the size of cations and anions are equal. In this case, for example, if I talk about KCl, if I talk about NaCl, this also Schottky defect, my friend. Now I am going to rub this part and we'll discuss the next one, my friend, Frankel defect. What is Frankel defect? It's very simple. When the cation leaves the lattice site and comes into the interstitial, that is voids, then this type of defect is known as, my friend, Frankel defect. What I am telling, when the cation leaves the site and reach the interstitials, then we can say this is known as, my friend, Frankel defect. Frankel defect are shows, for example, AgCl, AgBr, they show Frankel defect. Frankel defect are shown by those compounds which have low coordination number. Low coordination number, and the second one is the size of anion is more than cation, my friend. This is the case. Now the third one is, my friend, what is interstitials? Interstitials are treated as, my friend, voids. Voids are called interstitials. There are basically three type of void: triangular void, tetrahedral void and octahedral void. But if here given interstitial defect, then what will happen in this case? If the elements occupy, this comes in case of non-ionic solid. If the foreign material occupy the interstices like this, then this type of defect is known as interstitial defect. Due to interstitial defect, the density increases. What I'm telling, if the foreign materials occupy the interstices or voids, then this type of defect is known as interstitial defects, my friend. Now, what do you mean by absenter? This comes in case of metal excess defect. You remember, metal excess defect due to anion vacancy, due to anion vacancies. What will happen, that is the anion, the place are trapped by the electron, and this place is known as, my friend, absenter. What I'm telling, due to in metal excess defect due to anion vacancy, absenter, that is the electron are trapped by those sites where anion resides, and this, due to this absenter, there is a color in the crystal. So for color in the crystal, absenter is responsible, my friend. Clear to you? I think now you are very much familiar with these topics, and definitely it will help you a lot. Clear, my friend? So these are the few questions related to this chapter. So now time has come, time to say bye bye. Thank you so much.